Rich Report, a podcast with news and information on the world of startups and big data. Today, my guest is Tim Stay. Tim is from a company called Perfect Search. Welcome to the show, Tim.
Thank you very much, Rich. It's a pleasure to be here.
Yeah, Tim, we've heard a lot about big data in the past couple of weeks. I just came from the supercomputing conference, as I was telling you, where the thrust of the show was data-intensive computing, and it seems like big data is quite the buzz. So it really intrigued me to find out more about what you guys are doing.
Yeah, it was a great show. We really enjoyed being there. We were there as a partner with Fujitsu, and we've created an appliance with Fujitsu to search enterprise data in the cloud. We're really excited about the big data arena and feel like we have some real competitive advantages with big data. If you think about search and the challenges in big data around search is something that is extremely computationally intensive, and increasing data size only increases that computational demand. And traditional search engines have tried to keep their indexes in memory to take advantage of the superior horsepower in memory. But when they get to really massive size of data, being able to keep all of your indexes in memory becomes cost prohibitive because you just require so many pieces of hardware. So Perfect Search has looked at that problem and looked at the increasing amount of data. And something that David Bader, who's I guess one of the rock stars of HPC, recently said big data challenges require novel architectures for data-intensive computing. And that's really what Perfect Search has done. We've created a new search engine, and that's different than any existing search engine, and it's really based upon a unique architectural approach. And the key aspect of this that allows us to handle big data has been to reduce the total computations required to query a corpus of data. If you think about, here's one example of how we reduce the computation. If you think about a book index, and in the back of that book index, in the back of a book is an index that tells you the frequency and the location of a certain term. So a traditional search engine will create an index that's more like a list of words. On this slide, you can see Aaron and Alfred and Anne and Hank. These are all just single words of words. Perfect Search creates that same single index, but we also create patterns. We'll see that Hank and Aaron both are capitalized, and so that should be a pattern that probably goes together. And we'll create these extra patterns in the process of creating the index. And that seems to be a simple thing to do, but when you look at how traditional search will create sets of different terms. So we can look at Hitchcock and Alfred in 1899, which is when he was born, and we see that let's find the intersection of those terms. And the way that happens is by getting all the Alfreds. So first you have to crawl the data and identify all the Alfreds, all the Hitchcocks, all the 1899s, and then you start looking at the intersection of those different sets. And that can become incredibly computationally intensive when you start getting into the millions and when you start getting into multiple term queries. And so search engines will use things like B-trees and inverted indexes to help speed up that process. But even these can run into the billions of calculations very easily. And when you start talking about tens or hundreds of terabytes or even into the petabytes, it just becomes overwhelming for the number of calculations. Perfect Search, by creating these patterns, by creating these combination of terms, we can, instead of having the millions, we can have a few dozen or a few hundred of these patterns and be able to very quickly identify. So instead of using relying solely on B trees and inverted indexes, which could really bog down under big data. We use jump table, or it's really a modified hash table, plume filters, and some other acceleration tools that are patent protected to jump over the non-relevant data to the exact data. So we can avoid even having to do the intersection of those terms, and that can save billions of calculations. Often we can do the same query with 1% of the computational requirement, and that's part of what creates perfect search's clustering speed. On the next slide, we can show we have two more ways in which we gain some of that efficiency. We have a null query. In a traditional search engine, you still have to go through all of the Alfreds, all of the Hitchcocks, all of the 1313 to see, do I have any intersection with those? And you're spending billions of calculations. We can tell by looking at our patterns that there is no Alfred Hitchcock 1313 pattern with just a few calculations, with a few I/O reads, and that avoids billions of calculations. Also, if you have a multiple term query, for example, if you say I want to find Alfred Hitchcock, who was born in 1899 in London, by adding that term London, I now add the tens of millions of the London set, and I have to again find the intersection of all of those. By us having a pattern of maybe Alfred Hitchcock 1899 and Alfred Hitchcock London, I only have to look at the intersection of those two sets, and I can do that with a few hundred calculations instead of a few billion. This results in significant speed. This next chart shows a bar graph of perfect search doing lab results. We were both in Oracle's lab and in Microsoft's lab doing the speed performance against the same data set on the same hardware with the same queries, and we were anywhere from 10 to 1,000 times faster in these performance tests against these others, which were trying to take their indexes and find the data. And one of the things that Perfect Search can do that a database query engine might not do is they have to be limited to the number of indexes that they create, where we can index all of the fields and index if there's a character field or a clob or a blob, we can index all the content inside of there and still have this clustering speed, where they're limited to because of the cost of creating those indexes and maintaining them, they're limited to a few of the fields. It also has an impact on scalability. Google, again, because Google is trying to keep that index up in memory, they have to take a large index and spread it across a lot of machines. And Google does that better than almost anyone I know of. But the fact that it's a memory-based index means that there needs to be a lot of hardware. So if you start dealing with 1 billion documents, they need over 100 servers. We can do that same thing with just one server, and that might seem not very realistic, but when you think about, because we reduce the number of calculations, we can put our index on disk instead of having to keep it on memory. And the reason we can put it on disk, if we measured on one of these Oracle benchmark tests where Oracle did a query and they had over 1 billion I/O reads, we did the same query and we had about 370,000 queries. That was 3,000 times fewer disk I/O reads. So we can, because we've reduced the number of computation, we can be fast enough on disk to be competitive with traditional search engines. And again, if you think about if I'm relying on putting my index in memory, then if I have a 160 gigabyte index, I need 10 machines. If each one of them have 16 gig of memory. Where if I can put my index on disk, I can put that whole 16 gig on one disk if I've got a terabyte hard drive in there. And that's where we can have this 10 to 1 or 100 to 1 reduction in hardware costs and be able to allow us, and let's say it's not 160 gigabyte index, let's say it's a terabyte or a petabyte index, which the big data problem is this. You can see how it can become just cost prohibitive when you look at search for big data with traditional approaches. You have to have a different architecture, and that's what Perfect Search brings. We have another example of this is how much capacity we can put. If it's a memory-based system, then this is an example of a system we replaced. They had about 100,000 documents per server, and their CPU was maxing out. Because we could put it on disk, we got up to 1.6 billion documents on a single server, on the same server that they were using, and because we could store our index on disk instead of in memory, and our CPU was idling at around 15%. Perfect Search is really built for big data challenges. It's a novel architecture. It significantly reduces the computational workload. It allows for the index to be disk-based and still maintain a high query performance. The bigger index, we can have a bigger index stored per server. That single server can handle 10 to 100 times the amount of data, which means we can significantly reduce the total hardware footprint. And if we get to a certain size where we max out that one server, we can still parallelize the indexing and the querying, and we can implement Hadoop and these other approaches. But we can go so much farther before we have to implement those strategies on a single server. So we really feel like Perfect Search has a competitive advantage for big data, for cloud search, and for storage or backup, for computationally intensive searches such as semantic search or multiple join queries. Any of these areas where it really has significant computational requirements, we feel like we can be very competitive. And so we really believe that with this supercharged search engine, this last slide shows, the thrust of SSC breaking the sound barrier in one of the deserts out here in the West. That's what we feel like we can do. We're breaking barriers of big data, being able to search more, faster, better, cheaper, and greener with less hardware. And we'd love to be able to answer any questions if people have them by going to perfectsearchcorp.com.
Well, thank you for that, Tim. A question about SC11 and you were in the Fujitsu booth. What were you working with on them? Did they have a client that you both shared, or what was going on?
We were in their partner section as one of Fujitsu's partners of their booth, and Fujitsu has recently announced Nuvola cloud platform that allows companies to build a private cloud inside of their firewall with Fujitsu hardware with specific applications. And one of those applications in the new Nuvola cloud platform is the Perfect Search engine. So we can search the data that is stored in the cloud, the enterprise data. We can search email archives, database content, SharePoint repository, all of the things that they might want to store in the cloud. And so we're a partner, and Fujitsu is selling our appliance as part of this package of the Nuvola private cloud platform.
So, question, Tim, about using the Perfect Search software. We had a podcast guest who was complaining that you have to be a Boolean expert to write these queries, right? Big long strings to get the results you want. Does Perfect Search help with that?
Yeah, we have a very user-friendly interface that allows. We can either plug into an existing client's user interface, or we can provide one, and it allows you to do much like a simple web query, keyword. But if you want to have more advanced, we also can provide that functionality where we can provide boxes. Say, for example, on the patent database, we could have a box that says search only the author field, search only the patent number field, or the examiner field. And so that limits, it lowers the requirements of the user to have to remember all of the Boolean expressions, because you can go in and say, well, I want to find any patent between this range that was done by this examiner, and it's a simple fill in the blank instead of trying to remember all the complex expressions.
Sure. And then, Tim, I'm curious about how you engage with an existing IT infrastructure, right? Is it kind of seamless, or do you have to replace their database, or does your solution go in there and index this in the proper way to work with the software?
Yeah, we certainly wouldn't replace. We sit alongside a database or a data repository. We have an appliance approach, and the index would sit on our appliance. So it's really a benefit if you have a production database and you want it queried. That query index and query process can put a great load on your system. By offloading that work to our appliance, you're freeing up that those resources, so you're not interfering with the production or the responsiveness of your database while you're indexing or querying the database. So we would crawl it, and we have a way to schedule and throttle, how intensively the crawl happens. We create an index on our appliance, and then when queries come in, they're pegged against the index that we have stored on our appliance, and provide the search results back to them. And that frees up the database or the other data repositories from having to bear the burden of that processing.
So, kind of a wrap-up question here, Tim. I mean, you're an entrepreneur. You're a startup in an exploding space with big data. Do you guys think you're well positioned as data continues to grow exponentially, that your kind of solution will make sense for companies that want to find that needle in the haystack?
We do. 5 years ago, there may not have been the need for the power and the scalability that Perfect Search provides. But now it's not uncommon to have companies say, my data is growing by 400% a year. I'm now dealing with multiple terabytes and petabytes. And that just was unheard of 5-10 years ago. The search engines that were built 5-10 years ago are exceptional search engines, but they weren't built architecturally for this demand, and Perfect Search was built to handle this scale. And we feel like the features of the performance and the scalability are ideally suited for the challenges of big data search.
Well, terrific. Well, Tim Stay, CEO of Perfect Search, I'd like to thank you once again for coming on the show today.
It was a real pleasure. Thank you so much, Rich.
You bet. Okay, folks, that's it for the Rich Report. Stay tuned for more news and information on the world of big data.